All right, today we are going to concept and just kind of review a little bit linear regression as correlation. So correlation, pretty easy. I've got there's there that shows you the different types of correlation that we could have. First type of correlation is what we see here. And you can see that's just a whole bunch of data points in there. But you can see by the trend, and we've drawn a line of best fit in there to show the trend, that data seems to be moving like a line with a positive slope. So we call this positive correlation because it appears to follow a linear trend with a positive slope. The second one is what we call negative correlation for a very similar reason. The trend that you see in the data there seems to be following a linear pattern also, but a linear pattern that has a negative slope, so the line is going down. This last one here, there really isn't an up or down pattern to it, so we've kind of drawn a circle around it because we don't know what exactly the pattern is. When that happens, we call that no correlation. So that means there appears to not be a trend in that particular data. We've just got a whole bunch of random points there. So let's review here linear regression and how to find it. So in example 1, the data pairs that we have give the average speed of an airplane during the first 10 minutes of a flight. So X is in minutes, Y is in miles per hour. So 1 minute, 180 miles per hour. 2 minutes, 250 miles per hour, so on and so forth. So what we're going to be doing is we're going to be drawing a line of best fit. That's what we do with linear regression. So in order to do that, we need to actually plot these points. So we need to choose appropriate scales. So time after takeoff, that makes sense to count by ones because it only goes up to 10. So we can count by ones on our x-axis. You're welcome for already labeling it with the time after takeoff. Then speed of the plane already labeled for you. That's what Y stands for, but we need a scale there. If we look, the highest value that we see is 510. So we know that we need to make sure we go up above 500. So counting by 100s would leave us we'd be using less than half of the graph. So remember, you want to use as much of the graph space as possible that still fits. So 100s is probably too big of a scale to use. So I might look at 50s and see if that fits. So if we count by 50s, that means every second mark is 100. So this would be 100, 200, 300, 400, 500. So we'd be able to go up to 600, which is more than reasonable here. So we label every other mark at our hundreds here, then we have both of our scales done. Very, very important that you always label your scales and label your axes. We have to know what you're counting by, and we have to know what the variables stand for. So now it's just a matter of plotting points. So 180. So it's almost up to 200. But not quite. So right there's our first point. 250, that should be easy because it's right on a corner. 290, so very close to 300 there. 310, so just above my 300 mark. Number 5 is 400. Number 6 is 420. 7, 410. 8, 490, so almost 500. 9 is 520. And 10 is 510. Okay, so in order to draw a line of best fit, and it's going to be very difficult for me to do on here because I can't use a ruler, but I would suggest using a ruler or some sort of straight edge when you draw your line of best fit. Here's what's important about a line of best fit, because yours may not always be the same as somebody else's, but that doesn't necessarily mean it's wrong. It could be wrong, but it doesn't necessarily mean that it's wrong. The key is that a line of best fit needs to slope with the trend of the data. It also should have a similar number of points above the line as below the line. So we basically want to be going through the middle of the data. So you can kind of look here and see a trend. If I want it to go through the middle, I believe what I did was I connected these 2 points, so this one and when x is 2. Again, your line is going to look so much better than mine because I cannot use a straight edge on the screencast here. So this is going to be really sloppy. I apologize. I'm going to use a different color to try to make it stand out. But what you are doing is connecting this point to this one. And again, mine's going to probably look horrible. Hopefully not. Not as bad as I think it's going to look, hopefully. So we're going to go through and connect. Whew, not quite as bad as I thought. Again, you can use a straight edge, so hopefully yours looks a little more linear than mine. So what that does is it basically goes through essentially almost exactly through these 3 and these 2. So you end up, again, because I missed a little when I was freehanding it, you end up with 1, 2, 3 points below the line, 2 points above, and about 4 or 5 that are almost exactly on the line. So this is a good trend data. We've got 2 above, 3 below, so similar number of points above as below. So we need to select 2 points on the line and find its slope, because we're trying to find this equation so that we can use it. So the 2 points that I used were the 2, 250, and the 9, 520. Hopefully we remember how to find slope. We've just done that recently, but it's something you should never forget. So we've got x1, y1, x2, y2, so y2 minus y1 divided by x2 minus x1. So because we're using a real life situation here, it's okay to use a decimal. What you would get here is 270 over 7, and that's approximately 38.57. So that means that we've got a slope of 38.57. Now, it wants to know what the slope represents, because what's happening is we're taking 270 miles per hour over 7 seconds. So miles per hour, or minutes, sorry, miles per hour divided by the minutes, this is going to be the increase in speed. The slope represents the increase in speed per minute after takeoff. All right, use point slope form to write the equation of a line and then change it to slope intercept. Some of you don't like point slope form, and some of you use y equals mx plus b and you just plug in an x and a y. You can certainly do that as well. I always use point slope, but if you prefer that method and know how to use it, you can do that also. So I use point slope, so I'm going to do y minus y1. I'm going to use this one. So y minus 250 equals 38.57 times x minus 2. So I'm going to distribute over here. So that gives me 38.57x minus 77.14. So when I add the 250 to get y alone, I've got y equals 38.57x plus 172.86. So that is my regression equation. Using this equation, calculate the speed of the plane after 7 minutes in flight. So we're using the equation. So if I want to know what the speed is after 7 minutes, remember what my variables stand for. Minutes is my x. So I'm plugging in 7 for x. So 38.57 times 7 plus 172.86 is how I'm going to calculate that speed. So I'm sure you probably need a calculator to help you with that decimal multiplication. So when you multiply the 38.57 times the 7, you get 269.99, and then we still need to add the 172.86, which then gives us 442.85 miles per hour. Now, how accurate is the speed we calculated when we compare it to the value that's on the scatter plot? So we look on the scatter plot, and you can look in the chart too, but at 7 minutes we had 410 miles per hour. So basically, you've got a difference of 32 miles per hour. When you're talking speeds that are in the 400s, it's pretty accurate. So it's 32 miles per hour more. So we would say that that is fairly accurate. It is not a huge discrepancy. If you were off by 100 miles per hour, that would probably be a big difference. But 30 miles per hour is not a big difference when we're talking numbers in the 400s. It's a big difference when you're talking about the difference between 30 and 60 miles per hour. 30 would be huge, but here it's not such a big deal. G, use your equation to predict what the speed of the plane would be after 12 minutes in flight. So we're doing the same thing, just plugging in a different number. So when x is 12, we've got 38.57 times 12 plus 172.86. Now notice, this is why we do linear regression, because we just used the 7 to compare it to what the actual value was because we had a real life data point. Now here we're using 12 because 12 isn't on our data point. Once we have a model, in this case a linear model, to represent this data, we can use it to predict things that aren't in our data. So 12 minutes isn't in our data, but we can use this equation to hopefully find a prediction. So take your 38.57, multiply it by 12, it gives you 462.84, and then we still have to add the 172.86, and that gives us about 635.7 miles per hour is what it would be if it continued to increase. Now again, this information said during the first 10 minutes. So we don't know really what's going to happen. We could say that it's going to continue to be linear, but unless you know anything about speeds of airplanes, you never know. Maybe after it gets to the first 10 minutes, that's when it coasts and it doesn't increase anymore. The speed stays constant. We don't know what happens, but if it were to follow this pattern, 635.7 miles per hour is what we would have. All right, last thing we want to do, use your equation to predict how long the plane is in flight before it reaches 700 miles per hour. Again, assuming that it actually reaches that speed, which, depending on what type of plane we're talking about, it may or may not be able to reach that speed. But notice the difference between this in H and what we did in E and G. In E and G, it gave us a number of minutes and asked us to find the miles per hour. Here, it's giving us miles per hour and asking us to find the minutes. So in this case, it's giving us the Y value and asking us to find the X. So take our equation up here from D, plug in 700 for the Y, and then we will just solve it for X. So in order to solve for X, first we need to subtract the 172.86. So 700 minus 172.86 gives us 527.14. That equals 38.57x. So now we're going to divide both sides by 38.57. Which gives us, x is about, it gives us 13.667. So we could say approximately 14 minutes. If you left it, it doesn't say what to round to, so if you left it as, 13.7 minutes, that would be fine as well. Or if you said 13 and a half minutes, that would be okay as well. All right, so hopefully that refreshes your memory and you see our use for linear regression in real life situations. That is it for today.